Assalamualaikum warahmatullahi wabarakatuh. My name is Batrisha Balkis and I am going to present about the introduction of diene. Starting with its definition, diene is unsaturated compound containing two double bonds between carbon atom. Its IUPAC name is same as alkene by just changing the suffix from "-ine" to "diene". For example, in the figure, the carbon number 1 and 3 has double bond, so the name of this compound is 1,3-butadiene. Next, diene can be classified into three, which is cumulated, which is double bond is are adjacent, conjugated, which double bond are separated by one single bond, and lastly isolated, in which this is same as conjugated but it is separated by more than one single bond. Next, the overview of diene production includes the hydrohalogenation of dihalide, where halogen and hydrogen will be removed. Second is by dehydrohalogenation of diol, by removing water molecule, and lastly, steam cracking, which is an industrial process to manufacture diene. The application of diene includes the production of tire by polymerized 1,3-butadiene, second, production of rubber by polymerized isoprene, and lastly, diene is used as monomer subunit to produce complex polymer.
The chemical formula of diene. The chemical formula is CnH2n-2, where N represents the number of carbon atoms in the diene molecule. This formula indicates that a diene consists of two double bonds, hence the term di, and two fewer hydrogen atoms compared to an equivalent alkene with the same number of carbon atom. Dehydrohalogenation involves the removal of a halogen and hydrogen atom from dihalide compound, resulting in the formation of a diene. This reaction is typically carried out using a strong base, which abstracts a hydrogen atom from one carbon atom and a halogen atom from the adjacent carbon atom. This process generates a carbon-carbon double bond and eliminates the halogen atom. For example, let's consider 1,2-dichloroethane as the dihalide. When treated with a strong base like potassium at high temperature, one hydrogen atom is removed from one carbon atom and one chlorine atom is removed from an adjacent carbon atom, which will lead to the formation of a conjugated diene called 1,3-butadiene. Next, let's consider for 1,5-dichloropentane as the dihalide. While undergoing the same process, it will lead to the formation of an unconjugated diene called the 1,4-pentadiene. Next is dehydration of diol, where it involves the removal of water molecules from a diol compound, resulting in the formation of a diene. This process typically requires an acidic catalyst, which facilitates the elimination of water from the diol molecule and the formation of carbon-carbon double bond. For example, let's consider 1,4-butanediol as the diol. When treated with a strong acid catalyst such as sulfuric acid at high temperature, water molecules are removed from the diol into the formation of a conjugated diene called 1,3-butadiene. Next, when pentane 1,5-diol is treated with the same process, it will form an unconjugated diene, which is 1,4-pentadiene. Next is the elimination reaction of unsaturated alcohol and alkyl halides. Conjugated dienes can be prepared by the elimination of the unsaturated alcohol and alkyl halides, where in unsaturated alcohol, the catalyst used is potassium hydrogen sulfate. The acidic nature of KHSO4 facilitates the removal of water from the alcohol, resulting in the formation of a carbon-carbon double bond. In alkyl halide, the catalyst used is a strong base, like KOH. The base removes a hydrogen atom from the alkyl group, leading to the elimination of a halide ion, which is Cl- or Br-, and the formation of an alkene. This process is regioselective, thus leading to the formation of a more stable compound, which is the conjugated diene instead of the unconjugated diene. Next is dehydrogenation of alkanes or alkenes. Although not a common method, dienes can be synthesized from alkanes or alkenes through dehydrogenation. This reaction uses the chromium oxide or aluminum oxide catalyst and is typically carried out at elevated temperature.
Now I will present about the manufacturing process for the one of the most important diene, which is butadiene. About 95% of global butadiene are produced as co-product by the steam cracking of paraffinic hydrocarbon. The feedstock for this process usually consists of ethane, propane, butane, naphtha, condensate, or gas oil. First, the feedstock are combined with steam and cracked at the temperature of 790 to 830 degrees Celsius in the pyrolysis furnace. Pyrolysis, which contain hydrogen, ethylene, propylene, butadiene, and other important olefins, are produced during the steam cracking process. The reaction scheme for steam cracking process includes cracking of ethane to ethylene and hydrogen, formation of propane and methane from ethane, as well as cracking of propylene to acetylene and methane. Acetylene and ethylene from reaction before combine to form butadiene. Next, the pyrolysis from steam cracking is quenched to remove high boiling component, followed by compression to remove C5 and higher hydrocarbon, as raw pyrolysis gasoline and then dried in the processed gas dryer. The resulting product consists of mainly hydrogen and C1 to C4 compounds. Finally, distillation step is taken to separate the hydrogen, methane, and ethylene and other C2 compounds, and propylene and other C3 compounds, leaving the crude butadiene.
Thermal cracking is a process in which large hydrocarbon molecules are broken down into smaller molecules by heat. This process is used to produce a variety of products including gasoline, diesel fuel, and ethylene. In thermal cracking, alkanes are heated to high temperatures, typically in the range of 450 degrees Celsius to 750 degrees Celsius, and pressures up to about 70 atmospheres. This causes the bonds in the alkenes to break and the smaller molecules are formed. The products of thermal cracking are a mixture of alkenes, alkanes, and aromatic hydrocarbons. The products of thermal cracking depends on the type of alkene that is being cracked, the temperature and pressure of the reactions, and the presence of any catalyst. In general, the longer the alkene, the more likely it is to crack into smaller molecules. Let's have a look at octane. Octane is one of the many hydrocarbons that might be in the mix that is used to make ethene and propene. When the carbon-carbon bonds in octane break, the carbon atoms in the molecule are left with unpaired electrons. These unpaired electrons can then react with other carbon atoms or hydrogen atoms to form new bonds. This is why carbon-hydrogen bonds in octane also break and reform during the cracking process. Moving on to the limitations of thermal cracking of alkanes. First limitations is that it can be dangerous. The high temperatures and pressures involved in the process can cause explosions, and the products of thermal cracking can be flammable. Therefore, thermal cracking is typically carried out in carefully controlled conditions. Second, the products of thermal cracking can be harmful to the environment. Some of the products of thermal cracking, such as alkenes and aromatic hydrocarbons, are known to be harmful to the environment. These products can contribute to air pollution and smoke formation. Third, it is not as selective as other cracking processes. Thermal cracking produces a mixture of products, and it can be difficult to control the yield of specific products. This can make it difficult to meet the specifications of certain products, such as gasoline. And lastly, it can produce a significant amount of coke, which is a solid carbon residue that can build up in the reactor and reduce the efficiency of the process.
The latest technology of production of dienes is olefin metathesis reaction. It is the technology that used by splitting and regeneration of carbon-carbon double bond in olefin metathesis distributes fragment of alkanes. Olefin metathesis produces conjugated dienes from non-conjugated dienes. This is done by using a catalyst to break the double bond in one of the non-conjugated dienes and then allowing it to react with another non-conjugated dienes. As you can see on the left hand side, it is the illustration of reaction for olefin metathesis. It is used the olefin metathesis to produce desirable products of dienes by exchange the carbon-carbon double bond within the molecules. So what is the improved characteristics compared to the steam cracking? Here are 4 improved characteristics. The first one is about the selectivity. It offers high selectivity for the in production compared to the steam cracking and allows the formation of targeted synthesis of the specific diene products only compared to steam cracking that is generates a mixture of various byproducts. The second one is about the catalyst control. The metathesis catalyst influence reaction pathway compared to the steam cracking. The third one, it has improved in sustainability and environmental impact. It offers advantages in terms of sustainability and better environmental impact. It enables the utilization of renewable feedstocks such as biomass derived sources. The fourth one is the process complexity. Generally, it involves more complex reaction setups and catalyst systems compared to the steam cracking.
Olefin metathesis is a modern technology used in the production of diene, which offers several advantages and overcome the limitation of the traditional thermal cracking process. Firstly, olefin metathesis allows for the selective formation of specific diene. It enables the controlled rearrangement of carbon-carbon double bond in olefin, resulting in the desired diene product. In contrast, thermal cracking produces a mixture of product, making it too difficult to obtain a pure diene. Then olefin metathesis typically occurs at lower temperature and pressure compared to the thermal cracking, which lead to the reduce in energy consumption and operational costs. In addition, olefin metathesis also relies on catalysts that can be controlled to optimize diene selectivity, reaction rate, and product purity, which will allow for precise manipulation of the reaction. In contrast, thermal cracking lacks this level of catalyst control, leading to the less efficient and less specific diene production. Lastly, olefin metathesis is considered a more atom-efficient process as it conserves most of the starting material and generates fewer byproducts. This results in a more sustainable and environmental friendly production method compared to the thermal cracking. Despite the advantages of olefin metathesis, there are some potential disadvantages and the environmental effect associated with the latest diene production process. Firstly, the olefin metathesis often that relies on catalysts that require special handling, purification step or recycling process, which can add complexity and cost to the production process. Next, some catalysts used in the olefin metathesis may contain heavy metal that need for proper disposal or recycling of catalysts in order to minimize the environmental impact. In addition, while olefin metathesis generally operates at milder condition compared to thermal cracking, it still requires energy input for heating, maintaining reaction condition, and catalyst activation. Optimizing energy efficiency in the production process is an ongoing challenge to minimize the environmental impact.
Lastly, conclusion. Diene is an unsaturated compound containing two double bonds between carbon atoms. It is widely used in various fields as it is the starting tool to produce many synthetic products such as rubber. The synthesis of diene has been described as well as its industrial manufacturing, and the traditional and recent process also has been introduced previously together with its advancement, advantages and disadvantages. That's all from us. Thank you.